Good afternoon, everybody, and a very warm welcome to this webinar, the third and final webinar in a three-part series from the IMechE Tribology group covering the fundamentals and application of tribology. My name is Simon Edwards, and I will be moderating today's session. In previous webinars, we've covered topics of friction and wear, and in this session, we are now focusing on the topic of lubrication. And today we have two fantastic speakers for you, covering different perspectives from industry and academia. First, we have Gareth Brackie, expert technologist from Castrol, who will be illustrating tribology in action by sharing with us the science behind the latest MAGNATEC engine oil from Castrol. And then we have Dr. Mazen Al-Hajjar from DUALOCK and the University of Leeds, who will be sharing some topics on the tribology of joint replacement. So, without further delay, I'd like to welcome Gareth Brackie, expert technologist from Castrol. Gareth has over 20 years of automotive lubricant industry experience covering engine and vehicle testing, lubricant design and development, and product claims and demonstrations. Gareth specializes in the intersection of technology and marketing and the communication of technical benefits. And it is on this subject that Gareth will be speaking today, as he shares the science behind Castrol's latest MAGNATEC engine oil. So, thank you, and over to you, Gareth.
Hello, I'm Gareth Brackie, and I'm an engineer working in technology deployment for Castrol, BP's lubricant business. Today, I'm going to take you through an application of how we've used technology to solve a tribological problem. In this case, wear. Engine oils have been protecting internal combustion engines for well over a century now. And as engine design and vehicle usage has changed, oils have had to change too. Castrol identified an emerging trend of urbanization and the effect this was having on vehicle journeys and the associated effect on engines and oil requirements. More people living in cities and more cars on the road, all leading to more and more busy driving. As many as 18,000 stop-starts every year and many more in many European cities. This type of busy driving places additional stress on the engine and can lead to accelerated wear. To fight this problem, we've developed DUALOCK technology, a radical new molecule patented by us, working in combination with our existing intelligent molecules to create a powerful force field of protection, reducing engine wear by at least 50%. So, what is DUALOCK technology? It builds on the pioneering science of MAGNATEC's intelligent molecules that have been protecting against warm-up wear for over 2 decades. Scientists in Castrol's Research and Innovation Department have been working for years on anti-wear molecules, screening hundreds through key tests, finally arriving at the new molecule, which we call synovine. We still use our old friends, the intelligent molecules. These cling to critical engine surfaces and protect against warm-up wear. Our new molecule also clings to the surface, but much more tenaciously. And unlike the intelligent molecules, it doesn't leave the surface at temperatures over 80 degrees C. It's still there, protecting at higher temperatures, not even leaving the surface at 120 degrees C. What's more, working with experts at the chemistry department of the University of Cambridge, we found that when both the molecules are present in oil, they lock together at the surface. This forms what we call the powerful force field of protection. Firstly, we have our old friend, one of the intelligent molecules. It has a polar head and a hydrocarbon tail. At room temperature, it sticks to the surface in a flat, semi-ordered array. As the temperature increases, the hydrocarbon tail lifts up, and eventually, at over 80 degrees C, the molecule leaves the surface completely. Now we have our new molecule, synovine. It's much larger and a much more complex molecule, but still with a polar head group and a hydrocarbon tail. It also sticks to the surface at room temperature in a less ordered manner. As the temperature rises, its ordering might change, but it stays put. What is most interesting is that when both molecules are present in a specific ratio, something special happens. When the temperature reaches 80 degrees C, the intelligent molecule tries to leave the surface, but the synovine kind of reaches out and grabs it, keeping it on the surface. This is what we mean when we say they lock together. Both molecules remain on the surface, providing the layers of protection, the powerful force field. This is dual lock technology. So, how do we know this? As I've mentioned, we've worked with scientists at Cambridge University. We've developed state-of-the-art surface science techniques to look at what's happening on the surface with the molecules and how they're behaving and interacting. We've used the machine you see here, which is the SFG, which stands for Some Frequency Generation, that uses lasers to detect molecules on the surface and determine adsorption, ordering, and direction. We've even done this dynamically to simulate what happens in moving engine parts. We've also used atomic force microscopy to visualize what's happening. Images from the AFM are on my next slide. All of this work has informed you what I've told you about the molecules, and Cambridge have written a substantiation letter that supports our claims, and you can see that there. Here are the AFM images. The central image is the key one here. It is 1,000 nanometers wide. By contrast, a human hair is about 80 times this size, at 80,000 nanometers in diameter. You can see the flat areas. These are layer upon layer of our intelligent molecules, each layer about 1 molecule thick. Zooming in further, to the left, you can see the bumpy surface of the raw metal, steel in this instance. This image is 256 nanometers wide, about 100 times larger than a strand of human DNA. Using the same imaging technique on a combination of the two molecules, what we see is a complete coverage on this scale. Now a sea of synovine covers the surface, and these are the layers of protection that get in the way and provide the anti-wear protection. All of this is very interesting, but unless it provides a benefit to the consumer, what use is all this science? Well, I've said that it forms a protective layer, a powerful force field of protection. This gets in the way and reduces wear. And we know this as we've tested dual lock technology in real engines, in real engine tests that show it dramatically reduces wear. It performs very well in the Sequence 4A engine test that looks at warm-up wear. And it performs well in the OM646LA engine test that looks at stop-start wear, amongst many other things. The Sequence 4A test is from the American API oil standards, and it measures cam wear in warm-up conditions. It's an older design of gasoline engine with finger follower valve train design. This 2.4-litre four-cylinder engine powered a wide range of vehicles, from the Nissan 240 SX sports car to the Nissan Terrano SUV, and it's representative of older, mid-sized gasoline passenger car engines. The OM646LA engine test is from the European Resear oil standards, and it measures general engine durability, in particular cam wear. The test cycle introduces many aspects of modern driving, including low-speed operation, and it's the only test to incorporate engine-off sections to simulate modern stop-start or idle-stop systems. This makes it ideal for us to evaluate the wear effects of modern busy driving. The engine itself is a 2.2-litre four-cylinder diesel used in a huge range of Mercedes-Benz vehicles, from the C220D, often seen in taxi use in many cities, to the almost ubiquitous Sprinter van. And you can see in the graphs here the difference that dual lock makes. At least a 50% reduction in cam wear in both of these key tests. So why is this protection needed? Here we circle right back to the problem. For decades, MAGNATEC has protected against warm-up wear with its intelligent molecules. But if you look at the rest of the drive cycle here, when the oil is hot and the engine idles, or even restarts when fitted with idle-stop systems, there's a different problem. The loads on critical engine parts at idle can be up to 66% higher than on the open road, and the oil will be hot and thin. So you can see that different means of protection are needed. Other oils rely on zinc dialkyl dithiophosphate, or ZDDP here, conventional anti-wear that forms above 80 degrees C. And so do we. But we also have Synovine as part of dual lock technology. And as I've said, it sticks to the surface at these high temperatures and also stops the intelligent molecules from leaving. Hence, there's more protection on the surface, more stuff getting in the way of damaging wear. This is why you need more protection in modern driving, and why Castrol MAGNATEC with dual lock technology is so groundbreaking. To bring it all back together, we have a new molecule developed over years by Castrol scientists, patented and unique to us, that works in partnership with the intelligent molecules to form a powerful force field of protection. This force field of protection is called dual lock technology. This is how we describe all of this work in our marketing materials. Castrol MAGNATEC with dual lock technology reduces both warm-up and stop-start wear by at least 50%, responding to the modern problem of busy driving. Non-stop protection from every start. And there you have it. From fundamental science to the application of technology to a marketable product that we've been rolling out across the world and have recently launched in Europe. Thank you very much. Any questions?
Okay, thank you very much for that, Gareth. As you just said, I'd like to please now open for questions. We have about 15 minutes, and I'll do my best to ensure as many as possible are answered. So please go ahead and type your questions in the chat box, and then I'll field them to Gareth to be answered. In the meantime, while you're thinking of some questions, and I'm sure Gareth would welcome whatever's on your mind, so please don't be shy. But in the meantime, Gareth, I've got a question for you. You've shown how you've proven this technology works in the lab. Can you explain how you also demonstrate that it works in real-world applications?
Thanks, Simon. Yes, as I said in the presentation, we've tested it in numerous engines, as I described, and these are representative of real world conditions. They're real engines, but they are in the lab and they are on drive cycles. We have also run over 3 million kilometers of real world field trials across 5 countries. in various different conditions to fully understand the nature of the benefit and make sure that we're getting no harm. And I'm obviously pleased to say that we were successful across those 3 million kilometers. It's a very important part of our testing that we extend the lab into the real world.
Brilliant. Thanks very much. We've also got another question here from Irfan Abedi Esfahani. Irfan is asking, hi, many thanks for organising such a nice event. I wondered if there is a YouTube link or any other website to previous presentations. Irfan, there is a link to a YouTube channel, the IMechE YouTube channel. So you can search for previous events on the IMechE event hub as well. I don't know if you want to add anything, Emma, to that.
Yeah, no, I think this is Abi. Yes, these webinars will be available on the IMechE YouTube link. They might take a couple of days, but you will find them there. I've also just replied to Irfan with the link to last year's webinar on lubrication.
Brilliant. Thanks, Abi. Irfan, I hope that answers your question. Gareth, we've got another question here from Colin Warburton. Colin's asking, is it worth applying this product to my 44,000 mile car, or is it more effective from new?
That's a great question, Colin. And yeah, it is absolutely worth applying. I mean, you will get a greater benefit the sooner you start using it in terms of overall reduction in wear. But at 44,000 miles, there's plenty of life in the engine, and why not give it some more? So yeah, the molecules actually, absolutely will give you some benefit even on older engines. We've done quite a bit of work in the past, especially on our intelligent molecules, to verify that. And what happens is the wear rate drops very quickly. And we use that as the basis of a claim that it's never too late. So, I would say absolutely, it's never too late to use products like MAGNATEC and get that benefit and extend the life of the engine.
Great, thanks, Gareth. Next, we have a question from Graham Wilcox, and Graham is asking, how do you balance the benefits of protection against the need to reduce viscosity down to enable improved fuel economy?
Thanks, Graham. And that's one of the key challenges of the automotive and indeed much of the lubrication industry right now is the need to make oils thinner to drive fuel economy benefits. And when making oils thinner, you run the risk of reducing the durability of your oils, increasing the wear. And that's what we're doing in this particular instance. That's what we're doing with our additional molecules. We're bringing in more chemistry, more chemical effects at the surface to reduce this reduction in durability from thinner oils. Now we're applying MAGNATEC and Dual Lock technology across all our viscosity grades, but it is particularly key for the thinner grades, the 020s and 030s, and as we move even thinner. How we do it in this particular instance is we're adding more of the sacrificial wear material with our molecules, with our technology that allows wear rates to be reduced. In other areas, we'll be formulating with the base chemistry in a different way, but it's one of the key challenges, and it's why we keep doing durability testing and real world testing to ensure that whilst we get the fuel economy benefit with the fuel consumption reduction and the emissions reduction that is absolutely vital for modern vehicles, but we do so while maintaining engine life. You wouldn't want to give up on engine life because that's not if the engines wear out quicker, that's not good either.
Thank you, Gareth. Next, we have a question from Peter Lau. Peter is asking, thank you for your presentation. You mentioned 50% reduction in start-stop wear. Did you mean reduction in friction? Or you did the measurement in wear? If yes, how did you measure the wear? Thank you.
So thanks, Peter. That's a great question. No, in this instance we do mean wear. We measured the cams on the engines in different ways for each test. Basically, it's a surface profilometry measurement. You're looking at the cam surface across 7 points on the cam lobe for the Nissan test, the gasoline test, and for the 646, it's actually a surface profilometry across the whole cam profile, and then you measure the same measurements afterwards, and then you subtract the one from the other, and you can work out the wear. And for every lobe on every camshaft, you can sum up the total wear, and that's how we see a 50%, at least a 50% difference in that wear between oils with and without the molecules that we were talking about.
Great, thanks. Next, we have a question from David Neal. Oils are branded as suitable for petrol or diesel engines. What is the difference in engine characteristics that lead to this? And how are the oils themselves different?
Thanks, David. Again, that's a great question. So, in the past, obviously the diesel and gasoline engines are and still are very different fuel technologies, different injection strategies. In Europe, in particular, the move in engine oils has been to combine the specifications. So you tend not to get a specification that will only do gasoline or only do diesel. But what you might find is you'll end up with oils that are slightly better or much better, in fact, in many parameters for diesel versus gasoline or vice versa. And then we'll usually market those as such. A lot of it depends on what specifications you've put on the oil. The OEM specification in particular, some of these are more geared towards diesel or gasoline, depending on what the OEM has specified. And one of the main differences is the amount of soot in the combustion. There's a lot more soot in diesel combustion, and this can cause wear problems. It can cause other effects in the oil, and we're looking to have high dispersancy in order to maintain soot protection. Another big difference is in the use of, up until recently, diesels were the only sort of vehicles fitted with DPFs and after treatment devices that used to trap particulates. So we were designing the lubricants to have low amounts of elements that would poison or block these traps and catalysts. But now, with the stricter emissions requirements, even on gasoline, we're looking at manufacturers also including gasoline particulate filters. So we're having to make sure that we have the same low levels of these additive element chemistries in the oils as well for gasoline. So long story short is the oil specifications are separate, but they are converging for both gasoline and diesel as we get closer and closer to the minimum emissions limits.
Thanks, Gareth. We have 2 more questions here that are quite similar, so I'm going to try and bundle them into one. The first is from John Whiting here. He said,
Yep.
What are the fundamental differences between MAGNATEC grades, for example, A1 and C2? And then goes on to mention going from a 2.2 litre Duratal to a 3 litre V6 diesel. So I'm not too sure about the second part of that question, but I think it's fundamentally what's the difference between the different grades, A1, C2. And then the other question from Neil Cooper is, you mentioned an ASEA test spec. Can you advise the number and how it is different from other specs? For example, SAE, as the labels on motor oils seem to show a wide range of test specs. I think those 2 questions, Gareth, are exploring the different ASEA test specs and generally the different specifications we get on our products.
Yeah, I mean those are great questions, and they're sort of fundamental to the lubricants industry in Europe.
So Resear is the test specification body for Europe. It's the I won't try to remember what it stands for, but it basically specifies the test requirements in order to sell oils under these specifications, and they have a wide range of different ones. There are the A specs and the B specs, and A and B were diesel and gasoline, and they are now combined. So you won't get an A1 on its own. You'll get A1, B1. You'll get A3, B4 is a common specification, and then these are generally the what we would call high SAPs. Now this is the SAPs. It stands for sulfated ash, phosphorus, and sulfur, and these are the additive elements that are very useful for oil performance-wise, but unfortunately have the side effect of blocking some of these after-treatment devices, catalysts, and DPF filters. So there was a move to reduce the amount of these elements in oils in order to protect these devices. That led to the C classifications, so C2 and C3. And these oils fundamentally have less of these additives in, but obviously they still need to maintain the protection, as we've talked about before. So that there are additional tests in there to ensure that those specifications are met. But really, you're looking at the sulfur limits, the sulfated ash limits. It limits the amount of what we call TBN and detergent that you put in that will determine how long the engine oil will last, how it will cope with harmful combustion acids, etc. So we've got to maintain those limits while reducing the amount of what we would call good stuff in the oil. The difference within the A and C specifications is down to essentially how much fuel economy you can get as well. Some of the specifications will have stricter limits on fuel economy. You'll be allowed to use thinner oils, and it's important to understand these distinctions, because you wouldn't want to put a very thin oil into an engine that was designed sometime before that thin oil was even thought about, and then you could run into problems of excess wear, etc. So that's a very quick kind of rundown of what's different about the specific specifications. It could be a whole topic on itself, the difference between the specifications. And what we like to do at Castrol is use these specifications as a basis, as a jumping off point for our oils, and then we develop them not only to meet these specifications but to exceed them, as I've talked about in the presentation today. And we also have to meet and exceed the requirements of our OEM partners and customers. Each one, particularly in Europe, will have a specification of their own, often based on the Resear specifications, but with much more stringent requirements, additional tests, etc. So it's a very challenging industry, but it's very interesting to be able to formulate oils that meet and exceed these specifications.
Thanks, Gareth. And I mean, it's great. We've got loads of questions here, but unfortunately, we are running out of time, and we've got to leave enough time for the next subject. So I'll finish off with one more question here, and sorry to those who haven't had their question answered. There's a question here from Peter Hill. What regions of the engine have you seen reduced wear? I imagine, but don't know, that some parts will be much higher than 80 degrees C.
That's a great question. We focus in this particular product. The tests that we've used focus on cam wear, and there you're looking at bulk oil temperatures between 80 as you've just warmed up and to a little bit over 100. Yes, obviously in the combustion region, in the ring pack area, you're looking at much higher temperatures. And you do see ring wear, but it's a very different effect. We're looking at you'd be looking at different anti-wear techniques there. ZDVP would be the classic, creates a sacrificial phosphate glass on the surface, and that would be something that would be happening at temperatures in the ring pack region. But the work we looked at for today was the CAM region, and that's where these particular additives are used. Which is why I say we also rely on ZDVP in other parts of the engine, and then in bearings, etc. You're looking at the hydrodynamic properties of the fluid to create protection there.
Brilliant. Thank you very much, Gareth, and thank you for all of those questions. So next we're going to change topics, and we have Dr. Mazen Al-Hajjar, who is a staff research and test engineer in the Tribology group within the Research and Development Department of Diffuse Synthesis. He has over 12 years of research experience in the field of joint replacement in industry and academia, and he's also a visiting research fellow at the University of Leeds. With 20 peer-reviewed publications and over 70 peer-reviewed conference proceedings abstracts to his name, Dr. Al-Hajjar is perfectly placed to share with us the tribology in joint replacement, including advances in wear performance of bearing surfaces, development of advanced in vitro and in silico simulators, and wear debris and biological activity. So, without further ado, let me hand over to you, Dr. Al-Hajjar. Thank you very much.
Good morning, good afternoon, or good evening, depending where you are while listening to this talk. My name is Mazen Al-Hajjar, and I'm a researcher and a test engineer at Diffuse Synthesis, working within the Tribology group in our Leeds site in the UK. I also must acknowledge that I'm a visiting research fellow at the University of Leeds as well. I would like to thank the organizers for inviting me to speak to you today about tribology in joint replacement. I have been working in this field for over 12 years now, and my research mainly focused on tribology in hip joint replacements. So you will notice that the majority, if not all, the examples I give are specific to the hip joint. I will also not talk about fundamental tribology, as this has been covered by other presenters in this webinar series. In this talk, I will cover the advances in wear performance of bearing surfaces, development of advanced in vitro and in silico simulations, and I'll touch a little bit about wear debris and the biological activity coming out from these joint replacements. Typically, materials used in joint replacement bearings are ultra-high molecular weight polyethylene, metals such as cobalt, chrome, alloy, and titanium alloys, and ceramics such as alumina or zirconia, or even composite between alumina and zirconia ceramics. The manufacturing process used to create polyethylene implants has a dramatic effect on the characteristics of the resulting material. Also, a change in the manufacturing process typically has an effect on more than one characteristic, which is the reason each element on the slide, wear resistance, mechanical integrity, oxidative stability, is connected to the other two, creating a triangle. The most commonly studied characteristics are wear resistance, mechanical integrity, and oxidative stability. In our industry, we strive to develop manufacturing processes which deliver polyethylene materials with the optimal balance between these three elements.
Surface wear in joint replacement has to be minimized because the wear particles released by these joints would get accumulated in the surrounding tissue, and this over time may cause osteolysis and loosening of the joint replacement. Mechanical fatigue and delamination as well needs to be minimized. The images shown on the screen, the top one is a tibial insert of a knee replacement, and the bottom one is an acetabular cup of a hip replacement. And you can clearly see some oxidative degradation and reduction in mechanical properties over time of these implants. Irradiated, polymer chains are broken and free radicals are generated. When these free radicals are exposed to oxygen, A cascade reaction occurs in which the polymer chain is further degraded and more free radicals are generated. Gamma irradiation of polyethylene generates free radicals within the material which can react with oxygen and lead to reduction of mechanical properties, thus oxidation. Barrier packaging was designed to prevent oxygen from entering the package, allowing the material to maintain oxidative stability while on the shelf. During this time, recombination and/or cross-linking of the broken molecular bond is encouraged due to the lack of oxygen. However, once the package is opened, the remaining free radicals are exposed and may combine with oxygen throughout the life of the implant. Retrievals of implants that are barrier packaged, such as the GVF and ARCOM, have been shown to oxidize in the body. Oxidative degradation can be prevented by removing free radicals, and one way to do this is through heat treatment. Heating the material mobilizes the polymer chain, allowing the free radicals to recombine, as long as full combination occurs when the oxidation cascade cannot occur. During this recombination, cross-linking occurs. But the mechanical properties are also affected. This means that a compromise is required in defining heat treatment specification, and not all heat treatments are the same. So remelting, which is used by DePuy in our near implant, it brings the materials above its crystalline melting temperature. It eliminates all free radicals by providing them with enough energy to mobilize, recombine, and/or cross-link. Small loss of mechanical properties, resulting mechanical properties are well above the ASTM standards, and since the free radicals are eliminated, oxidation is less likely to occur, providing the confidence that the mechanical properties will remain at a constant level over the life of the implant. Another way is annealing. It brings the material to a temperature just under its melting temperature. Increased thermal energy resulting in increased molecular motion. The increased motion of the polymer chain helps promote additional reactions between free radicals. However, because the crystalline regions have not melted, the polymer chains do not have unrestricted mobility, and thus all of the free radicals are not eliminated. Because the material is not just subjected to its crystalline melting temperature, there isn't as much of an effect on the material's mechanical properties. However, because free radicals still exist within the material, oxidation may occur over time, which results in a decrease of mechanical properties. This process is used by X3 polymer components. And we know that heat treatment improves wear properties. And you can see gamma irradiation and heat treatment improves wear properties and oxidative stability. However, it reduces mechanical properties. The use of antioxidants is another way of eliminating free radicals, and they are used as alternatives to remelting or annealing. The evolution of this next generation is driven by the need to retain the crystalline properties while preserving the oxidative stability of the molecular chains upon irradiation. The doping agent used to date are antioxidants, which neutralizes the free radicals created during gamma irradiation without the need for heat treatment. The elimination of heat treatment reduces the decrease in mechanical properties as seen with both remelting and annealing, but maintaining the good mechanical strength and wear properties of the polyethylene material. On this graph, you can see how accelerated aging over time does affect the oxidation index for some polyethylene material. And you can see that the antioxidant polyethylene maintains its oxidation index at a low level, even under accelerated aging of up to 40 days compared to gamma irradiated polyethylene or not irradiated polyethylene at all. And you can see on this slide how the wear properties of the antioxidant or the heat-treated, the remelted polyethylene materials produces lower wear rates than the standard GVF material. And when you look at the polyethylene and hip replacements, you can see a huge reduction in wear rate when you compare the Marathon, which is moderately cross-linked polyethylene, to the Ultrex, which is a highly cross-linked polyethylene. And when you look at the overall picture, you can see a huge reduction in wear rates of the Marathon, the Ultrex, and the antioxidant polyethylene compared to the non-cross-linked polyethylene or the conventional GVF polyethylene materials. When we focus on the antioxidant polyethylene, you get a reduction in wear rates. However, you get a very good oxidative index even under accelerated aging, as I showed before. So it preserves that mechanical properties of the conventional polyethylene, but you get the benefit of reduction in a huge reduction in wear rates of the polyethylene material. Moving to ceramics, another biomaterial that's used in joint replacements, mainly in hip replacements. They come in alumina, zirconia, or alumina and zirconia composite. The alumina ceramic on ceramic was first used by Butin in 1970 as a hip replacement bearings. And the ceramics were first used as a biomaterial in 1932. And they have other uses. Alumina has other uses. They were used as dental implant, partial tibial plateau, total knee replacement, even on the femoral component, ankle prosthesis, and finger joints. The reason they are used because they have high hardness, they are scratch resistance, they have low wear properties, very corrosion resistance. There's no metallic ions released from these ceramic materials. They have dimensional stability and good mechanical strength. You can see on the slide now some SEM images of alumina ceramics. Even though alumina has been used since the 1970s, the manufacturing processes has changed dramatically. And you can see the SEM image on the top image is an SEM of a first generation alumina ceramics used in hip replacements. The middle image is from the second generation, and the third image is from the third generation isostatic hip ceramic materials. And you can see that the grain size is getting smaller and more uniform. Further improvements in ceramic materials utilizes the good toughness of zirconia and the good hardness of alumina ceramics. And you end up with a composite of alumina and zirconia oxides where the zirconia act as crack dissipation when it's initiated within the alumina matrix. And this is an illustration of a zirconia toughened alumina structure showing how the crack is dissipated by the platelet or the zirconia particle when it's initiated within the alumina ceramic. Ceramics is used as a femoral head articulating against the polyethylene material. And in this slide, you can see that the wear rates of a ceramic on polyethylene material is lower than the wear rate of a metal on polyethylene material, indicating the benefits of using ceramic femoral head compared to metal heads. Ceramic is also used as a ceramic on ceramic bearing, as a hard on hard bearing, and is usually shown a superior tribological performance. Ceramic on ceramic under a standard walking cycle produces wear rates lower than 0.1 millimeter cube per million cycles, compared to 5 to 10 for cross-linked polyethylene and also 35 to 50 millimeter cubed in metal on conventional polyethylene material. In addition, the wear particles generated by the ceramic on ceramic bearings are usually less biologically active because there is significantly lower amount of these particles released by these joints. Now I'm going to talk about advances in vitro and in silico simulations. Wear, material fatigue, loosening, squeaking, corrosion, biological reactions such as osteolysis are all clinical outcomes. And they are all output of a combination of different scenarios that may occur clinically. And it's usually a combination of implant surgical position, implant design, surgical variation, or patient variation. Such conditions come together to create conditions unfavorable for a joint replacement, causing high wear, causing squeaking, causing corrosion, or loosening, fatigue, or even reaction to these debris coming out of this implant. Thus, we have been, over the years, we've developed advanced in vitro and in silico simulations to try and simulate these conditions and test our implants under such conditions to make sure that they are safe and reliable in patients. Some of these changes are oxidative degradation of polyethylene by inducing accelerated aging, third body head roughening of the femoral head or the acetabular cup, looking at how different head sizes affect the wear, using different loading regimes such as activity of daily living and simulating stop-start motion or stop-dwell-start motions, stair climbing, stairs descent, different activities. Trying to see how size, weight, offset, variation in lubricants, and how the biological reactivity and sensitivity is affected by different patients. And also looking at different surgical delivery and component positioning to see what's the effect of rotational malpositioning or translational malpositioning or even variable offsets have on the outcome, such as where the tribology of the implant. And some of the examples that we have is if we apply a stop dwell start cycle of one walking cycle, 10 seconds dwelling, and then starting again, you can actually increase the wear rate of a metal on polyethylene or a ceramic on polyethylene bearing compared to actually testing it only under standard walking cycle. And you can see that the wear of polyethylene increases when articulating against a damaged head or a roughened head compared to a smooth head. It's been shown that applying a translational mismatch between the femoral head and the acetabular cup would lead to dynamic separation and edge loading scenarios where the femoral head contacts the edge of the acetabular cup, causing inferior tribological conditions where the wear of, for example, a ceramic on ceramic would increase significantly compared to a well-positioned implant. And you can see that the combination of a translational mismatch with a steep comp inclination angle would increase that severity of edge loading even further, causing further increasing the wear rate of such bearing material. So such combination of different scenarios would lead to different tribological conditions that we should, as well as improving on the material properties, we should improve on surgical techniques and positioning of these implants. And you can see that with this example in vitro studies that showed that the wear rate of a ceramic on ceramic bearings with 4 millimeter mismatch with 45 degrees inclination angle produced a wear rate of 0.3 millimeter cubed. But if you apply that 4 millimeter mismatch with a 65 degrees inclination angle, you increase the wear rate to almost 1 millimeter cubed per million cycles, a significant increase in wear rates. There has been advances in silico simulations as well, trying to simulate dynamic separation and edge loading in total hip replacement under variations of component positioning. This work was completed by Achilles et al. And Jahani et al. In 2018. Squeaking was also simulated on these simulators, and not just audible squeaking, but also vibrations were detected using accelerometers that corresponds with edge loading on these simulators. Advances in geometric wear measurements were also made, and what the image here is showing the pattern of the volume change on a polyethylene liner in a hip replacement, showing where the location of that wear and deformation under different in vitro conditions, simulation conditions. The first column showing standard concentric conditions, the middle column showing a mismatch, a low level of mismatch between the femoral head and acetabular cup causing edge loading, but a 4 millimeter mismatch with a 65 degrees inclination angle causing a severe edge loading with a significant increase in wear and deformation at the rim of the acetabular cup. Now I'm going to talk about wear debris. As the joint articulates where particles are formed at the interface from the softer material, particles are phagocytosed by macrophages in the periprosthetic tissues, which result in activation of the macrophages and release of the inflammatory cytokines. And this is a drawing, cartoons of some of the mechanisms that the particle goes through of different sizes in the macrophages and the release of cytokines to bond resorption. This is an example of ultra-high molecular weight polyethylene debris seen under the SEM. And these more polyethylene debris with different size and shape, and what we call them, these are like fibrils and small granules of polyethylene material released by the implant. This is an image of a metal particles. Usually they are an order of magnitude lower than ultra-high molecular weight polyethylene. The particles are usually clumped together because of the protein surrounding them from the lubricant, and they are usually difficult to size because they are clumped together. This is another image, but from a ceramic particles, and they are usually clumped together like the metal, but they have different sizes and shapes. And you can see this one has micron-sized and nano-sized particles in this image. Things we need to know about wear debris is the volume, size, number, and characteristics of the wear debris present. We need to know about the biological reactivity of each wear debris at different size, volume, number, and composition, and also capacity to predict functional biological activity of prosthesis in vivo from wear rates and particle characteristics. For example, key facts about ultra-high molecular weight polyethylene. Simulation with particles in the phagocytosable range 0.1 to 10 microns caused elevation in cytokine release. Submicrometer particles are the most biologically active. The major oscillating mediators were TNF-alpha, PGE2, and IL-6. Differences in the response of murine and human macrophages to the different type of particles can be explained by the different particle morphologies. Particle size and volume are critical factors in macrophage activation, and the heterogenic response to particles suggests that this may be an important factor in determining implant life. So this is how you see that the knowledge we gain about the particles themselves can be a predictor of implant life. I would like to thank you very much for listening, and if you have any questions, I'm ready to answer them. Thank you.
Thank you very much, Dr. Al-Hajjar. So yes, over to questions now. We have some come in here. So the first question we have is from K. Shiraj. How can we calculate oxidation index?
Thanks for that question. There is a method, the FTIR method, is commonly used to actually calculate that oxidation index of polyethylene. It does involve damage, like destroying the sample, where you actually section it and take it through the process to actually measure that oxidation index.
Okay, thank you. We have another question here from Neil Cooper. You mentioned biological reaction from the oxidation of polyethylene. Are there any issues with biological reaction from adding the antioxidant molecule to the material?
This is something that we tested, and we did compare the biological reactions. And what we look at is the debris, the size and shape of the debris coming out from an antioxidant polyethylene compared to non-oxidant antioxidant polyethylene, and also look at the biological reaction. And the in vitro studies that we did showed no significant difference in that biological reaction of that antioxidant polyethylene compared to the cross-linked polyethylene.
Okay, thanks. Question here, are ceramic on ceramic designs lubricated? If so, how? This is from Stephen Kirkham.
So we don't. We depend on the lubricant within the body to actually add that lubrication to our bearings. What we call after the surgery, something called the pseudosynovial fluid, and we depend on that for our bearings, for our hip bearing or knee bearings to actually be lubricated and work clinically. But we don't add a lubricant to the bearing itself.
Okay, thank you. And a question here from Colin Warburton. I am at the back of a long list of people for a new knee. What material do I ask the consultant to use?
So for the knees, there are limited availability. The most commonly used material combinations is a cobalt chrome femoral component with a polyethylene tibial insert and and typically a titanium tray. I would, as I'm from diffuse sensitive, I would say ask them for the Attune, which is our latest knee replacement.
Thanks. Another question here from Navina Nadakrishnan. Thank you for the nice presentation. I'd like to know, is there any surface coatings that have been employed on the hip and total disc replacement in order to reduce the wear of implants? If so, what are the coatings being used and how commercially available are they? So I have reduced that question a little bit, so I hope I've still got the essence of that. So it's around coatings used in these devices.
Yes, many companies have attempted to add coatings to the implants. There are implants available on the market with coatings, and they are usually to actually try and reduce the wear of the implants. There is also reluctance to using some coatings on bearings. I don't think we have achieved the optimal coating to actually serve the purpose of reduction in wear rates. We have improved the material drastically to reduce the wear rates of these bearings. I hope that I answered that question.
Thank you, Dr. Al-Hajjar.
Yeah.
That's great. We don't have any more questions, and also we're pretty much out of time anyway. So what I'd probably like to say is a huge thank you to you and also to Gareth as our speakers. I mean, without both of you today, this event would not have been possible. So a huge thank you. I'd also like to say a big thank you to Abi Oladokan, who has been a tireless organizer behind this series of webinars. And of course, thank you to the team at the IMechE for making this event possible online. So thank you very, very much. Also like to say a big thank you to all of you who have joined us today. I wish you a great rest of your day and hopefully see you at the next Tribology group event, which will be the Donald Julius Gruen Prize Lecture on the 4th of December. All details are available on the IMechE website. So thank you very much and have a great day. Goodbye.